Today, I want to talk about the multiplication and division of complex numbers when they're written in modulus argument form. Well, firstly, I want to remind you of what we did in the last video, which was Euler's relation. There are several very strange things around when you're dealing with complex numbers, and the fact that e to the I theta is cos theta plus I sine theta is just one of them. I hope by the end of this video to have convinced you that this is a very nice way of looking at things and saves a lot of rather tedious algebra. Well, I said I was going to speak about multiplication and division. Let's look at multiplication first. If I take the multiplication of these two numbers, well, if I write them in exponential form, r1 e to the I theta 1 times r2 e to the I theta 2, they're very, very easy to multiply together. r1 times r2 and e to the I, add the arguments theta 1 plus theta 2. I can write that back in the trig form, if you like, r1 r2 times cos theta 1 plus theta 2 plus I r1 r2 sine theta 1 plus theta 2. A very simple little piece of algebra. We're just multiplying numbers and adding indices. You can do it if you want in the trigonometric form, and there it is. Multiplying together, you get cos I squared sine sine, so that's minus sine sine cos times I, cos sine times I. Then your trig formulae, cos theta 1 plus theta 2 is cos minus sine sine theta 1 plus theta 2 is sine cos plus cos sine. Simpler. I certainly would prefer to use the exponential form. Well, what happens when we look at division? If I want to divide two complex numbers, well, let's put those into r1 e to the I theta 1 divided by r2 e to the I theta 2. That is going to be r1 over r2. How do you divide? You subtract indices. And so we get r1 over r2 cos theta 1 minus theta 2 plus I r1 over r2 sine theta 1 minus theta 2. And that you can do with sines and cosines. It doesn't quite fit on the page the way I've done it, because it's a lot more algebra. One over the other, we need to multiply top and bottom by cos minus I sine, so we make the bottom into a real number. Cos minus I squared sine sine cos minus cos sine, both times I. Cos minus I squared sine sine. They're all the same angle there. So you just have 1 on the bottom, and now you have r1 over r2 cos theta 1 minus theta 2, so on. I want to draw your attention to two things here. One, when you're multiplying two complex numbers, one with modulus 1 and one r1 and one with modulus r2, they have modulus r1, r2. So the modulus of z1, z2 is mod z1 times mod z2. And when you are multiplying them, you start with an argument of theta 1 and an argument of theta 2. You finish with an argument of theta 1 plus theta 2. So arg of z1, z2 is arg z1 plus arg z2. That is something that you are expected to remember. You should be able to see what's going on with division. When I divide, if I divide Z1 by Z2, Z1 had modulus R1, Z2 had modulus R2, Z1 over Z2 has got modulus R1 over R2. So that's just mod Z1 divided by mod Z2. And if you look at the arguments, the argument of Z1 divided by Z2 is θ1 minus θ2 is arg Z1 minus arg Z2. I've summarized all that for you. There we are. So here are the results for multiplication, division, multiplication, division. And here is just the way that you can write it down. The exponential form, you don't have to learn any answers, they're just here. Let's look at an example doing this. Z1 is 8 cos pi by 3 plus 8I sine pi by 3. So that has modulus 8 and argument pi by 3. Z2, so it's 8e to the I pi by 3. Z2 is 4 cos pi by 6 minus 4I sine pi by 6. When we are dealing with modulus argument form, between the cosine and the sine, there must be a plus. That is the essential thing about modulus argument form. So this one was nicely in modulus argument form, this one isn't. How can we turn Z2 easily into modulus argument form? That minus is in the way. Sine of minus pi by 6? What's cos of minus pi by 6? Well, your trig should be up to the idea that cos of minus pi by 6 is the same as cos pi by 6. And sine of minus pi by 6 is minus sine of pi by 6. So if I want these two lines to be equal, I must put in a plus. Now I have written Z2 in modulus argument form. So now I can write it in the exponential form, 4e to the minus I pi by 6. So that's the first part of the question. Second part, find Z1, Z2. Z1, Z2 is 8e to the I pi by 3 times 4e to the I minus, well, perhaps I'll put the minus there, minus I pi by 6. Don't have to think at all. 8 times 4 is 32. How do I multiply? I add the indices. If I add pi by 3 and pi by 6 minus pi by 3 minus pi by 6 is just pi by 6. So that is e to the I pi by 6. And Z1 divided by Z2, just as easy, 8e to the I pi by 3 divided by 4e to the minus I pi by 6. 8 divided by 4 is 2. I subtract minus pi by 6, that's pi by 3 plus pi by 6, that is pi by 2. So this is 2e to the I pi by 2. We could take that last one a little bit further. If we have a complex number with argument pi by 2, that's where it is. So this is just 2i. But we were asked to write it in the form 2e to the I pi by 2, so that would be the answer to the question. This is just simplifying it. So easy when you have the exponential form, when you're using Euler's relation. Do please get used to it. It's well worth it.